Okay, carrying on from where we were in the last exciting video. I'll see if I can splice these together, but that's like work. It's like, I don't do work, I just do math. Math is fun, work is not fun. Okay, looks like I need my create a common denominator pen here, everyone. So I'm gonna multiply this one. Thank you. Aren't interruptions lovely? I just like hate interruptions more than I need to. I need a common denominator, so I get out my common denominator creation pen. If you don't have one, you can go buy one. It's an excuse to go to the dollar store and also get yourself a $1 chocolate bar. Okay. What? You don't just look for excuses to go to the dollar store? Oh.
I kind of hate the dollar store. You hate it? I love the dollar store. I don't like the smell. That's fair.
There. Hey, did you know that 1 minus cos squared x is equal to something else? What else is it equal to? There's a hint. Yeah, there's a hint on the other side. It's sine squared x. So we're done. Well, we just have to write it out.
Snow? Oh, snow. Why would I say snow?
Guess what? It's fancy time.
Is it QED?
Boom. Yeah, we did it, everybody.
Wait, he killed a cow?
Everything okay?
They was asking me about my locker because I took my lock off.
Oh.
I said, I needed
Well, that's great. I'm glad they called you down and interrupt the lesson for that. Okay. Let's keep going, everybody. Any questions about this one? It's pretty straightforward. Okay, let's go. All right. Prove it. Do you need to see this one proven?
Yeah.
Yes? Okay. All right. Okay. Looks like the right-hand side is already pretty simplified. So let's do the left-hand side together. The left-hand side is equal to secant theta. Hey, great news. This one's in terms of theta. This one's just like some fractions. All right. So secant is 1 over cosine being divided by cosine, which is cosine theta over 1. Like, that's just a fancy way of writing down that one with its denominator. Because people are going to say, how did you get to 1 over cos squared theta? And I'm going to say I just flipped and multiplied. Okay. So then minus tan is sine theta over cosine of theta. And it's being divided by what? Cosine of theta divided by sine of theta. Cool. All right. Now we're going to flip and multiply, right? We're going to keep flip change. We're going to finger licking this fraction. So this one here, we flip and multiply that one. So that's equal to 1 over cos squared theta. This one we flip and multiply that one. So that's minus sine squared theta over cos squared theta. Okay? Let's flip and multiply there. People are following along? That's okay? Good. So this is equal to, apologies for working horizontally, but hey, life moves pretty fast. 1 minus sine squared theta over cos squared theta. Anyone getting heebie-jeebies about that? What's 1 minus sine squared theta equal to? Cos squared theta. What's something divided by itself? 1. Did you know that I'm 46 cos squared theta divided by cos squared theta years old? Yeah. It's fancy time, everyone. Whee! Oh, whoa, what happened? I just grabbed I just accelerated to the next example. All right. Okay, you want to see this one too, everyone? No, we're going to skip it. Okay, I can go back later and do it, but for now, we're going to skip that one. Okay, here are some new. This is new now. That was all review from grade 11. That's just write things in terms of sine and cosine and discovered that the left side equals the right side because your teachers are not doing you dirty. Okay, so in this case, we actually have some new identities to learn. And again, If you choose to bring a cheat sheet to the test with your identities written on it only, that will be acceptable. If you decline to bring a cheat sheet to the test and instead commit to committing these to memory, then that's worth a bonus mark. Ooh. Up to 100%. I can't go above 100%. Okay, so recall that sine A plus B equals sine A cos B plus sine B cos A. But what if A equals B, you ask? Well, that would be the same thing as saying sine 2A. That would be equal to 2 sine A cos A. Because these two darn things would be the same thing, wouldn't they? And we just add two of them together, and oh, would you look at that. There's only really one new thing to memorize, and that was your compound angle theorem from before, and it includes your double angle. Okay. Now, the cosine ones, why the heck are there 3? Ain't no but. Well, maybe you are the type that likes to memorize rearranged versions of the same thing, but they're all just rearranged versions of the same thing based on your Pythagorean identity. Cos squared theta plus sine squared theta equals 1. So this one is just like a substitution there. We substitute in, we get like the 1 and it adds an extra cosine, or we have it in terms of sine. You know, so I can't be bothered to memorize all that stuff. I can't even be bothered to memorize my double angle. I just memorize the compound angle because it covers all of the conditions. So let me prove that to you with the power of math. Recall that cosine A plus B equals cos A cos B minus sine A sine B. Okay? But what if A were B, you asked? Well, that would be cosine 2A. Okay? And that would equal cos A times cos A, because it's the same thing, so cos squared A minus sine squared A. And then we get all of our special rearrangements of this, because you have like cos squared A plus sine squared A equals 1. So that is to say sine squared A equals 1 minus cos squared A. So if I put that in there, then you have cos squared A minus, put it in brackets, 1 minus cos squared A, which is a fancy way of saying 2 cosine squared A minus 1, because minus a minus is a plus. Okay? All right, so that's how you would rearrange those. This one might be worth memorizing on its own. You can still build it with your double angle theorems. It's not that bad. It's not that bad. I'll prove it to you. I'll prove to you that it is not that bad. With a fresh copy. Okay. Tan 2 theta is equal to, let's get a pen that doesn't make me feel like it's crayon. Okay, that would be sine 2 theta divided by cosine 2 theta, which is a fancy way of saying this is 2 sine theta cos theta over, well, cosine 2 theta, that would be, we can write that in terms of sine here. 1 minus 2 sine squared theta. And we can manipulate this to get back to this if we really want, in a variety of ways. I would not be going through this in any proof myself, because I want to phrase this in terms of sine and cosine anyway. So I would always be getting to something that looks like this and changing it around in some way to make it more meaningful to me. Okay, let's keep going. So,
I already told him Alex.
let's prove this one, everybody. Okay, our left side is already pretty well organized. It's already in terms of sine and cos. So we're going to be working the right side in this proof. The right side is equal to so cosine 2x is equal to, we are going to write that as cos squared x minus sine squared x. That is cosine 2x plus 1. And then we are all over sine x, sorry, 2 sine x cos x. All right, cool. Now, what we can do is note that we have something that ought to give us heebie-jeebies on the top here. Something that gives us a real nice substitution. Let's rewrite it as 1 minus sine squared x plus cosine squared x all over 2 sine x cos x. Anyone got heebie-jeebies here? What have I shown you? That's just cosine squared x. So I have cosine squared x plus cosine squared x all over 2 sine x cos x.
Oh, I know.
Whoop. Well, something plus itself is just 2 times that thing. So that's my numerator, divided by 2 sine x cos x. Cancel, 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 cancel. Equals cos x over sine x equals the left-hand side. And the people rejoice. That's a grade 12 level one. Got to remember a new identity and apply your old identities. Nothing old gets discarded, but lots of new things get added. Okay, let's go. That was a fun one, wasn't it? That was great. Okay, here we've got left side and right side stuff to tidy up. So we're going to go left side is equal to cosecant to x, which is equal to 1 over sine to x, which is equal to 1 over sine x cos x, but I got 2 of them. 2 sine x cos x. Okay, left-hand side can't be simplified any further. This is just me applying the now memorized identities. Actually, you can kind of see me calculating in real time. All right, and then the right-hand side. This is equal to cosecant x divided by 2 cos x. All right, well, what's cosecant x? That's 1 over sine of x over 2 cosine x. We are going to flip and multiply. That's all over 1. When I flip and multiply, that's 1 over 2 sine x cos x. So fancy. Do I lose anyone here? Is it better if I show it this way? This equals 1 over sine x multiplied by 1 over 2 cosine x. And just like write that out and then go to this line. Maybe that would be a little better, but it's the same. I think it's okay. Okay? Cool. It's just flip and multiply. Okay. All right. Okay, tan x plus cotan x. How exciting. The left side equals, if you went straight to sine x over cos x plus cos x over sine x, I'd be okay with that. But if we do that, maybe leave space. Oh, why won't it erase? That's annoying. Oh, there it goes. That's weird. It's just a thing. Leave a little space because we're going to want to create a common denominator here. Multiply by sine x over sine x. Multiply by cos x over cos x. And that is our left-hand side. So we have sine squared x plus cos squared x. Hands up, you got heebie-jeebies? So that is our left-hand side, which is equal to 1 over sine x cos x. Let's see what happens when we work the right-hand side. 2 cosecant x, sorry, 2 cosecant 2x. Gavin?
Just for the left side.
Yeah?
Are you just like allowed to multiply the fractions by like sine x over sine x and cos x over cos x?
Do you know that I'm 46 sine x divided by sine x years old?
Yes.
For all values of x? Except for pi and 0 and any other multiple of pi. Yeah. What's sine x divided by sine x?
1.
Yeah, so am I allowed to multiply by 1?
Yes.
Yes.
Okay.
Yeah, so I'm just creating a common denominator there. So I am allowed to like add or subtract 0, or like add something that adds and subtracts to 0. That's like a classic complete the square type math move that you're always allowed to do. And then you're also allowed to multiply by 1. But when you multiply by 1, you should be careful that you're not multiplying by 0 over 0. That's why I said I am 46 sine x over sine x years old when x does not equal 0 or pi or 2 pi or any multiple of pi. Because that would make me 0 over 0 years old, and I don't want to live in that world. I don't know what that world entails. Okay, it's like another dimension. Okay, so let's keep going. Okay, 2 cosecant 2x. This is equal to 2 over sine 2x. Cosecant is just 1 over sine. So this is 2 over sine because, hey, we got a 2 there. Okay, 2 over sine 2x. Well, let's apply our identity. This is 2 over sine x cos x, which is equal to 1 over sine x cos x. Okay? We good there? Yay! Okay, now that's all the identities practice that I'm going to do today, but I do need to show you some solving equations using these identities practice. Yay! We get to solve equations, everybody. Yeah, we're solving equations. So, when we're solving a trigonometric equation, we're finally going to take that skill we started developing in grade 11 and now apply it to some solve type questions. The reason this is important is because we want to express all of our trigonometric ratios in terms of the same ratio. Okay? So we're going to need to use trigonometric identities to manipulate our equations so they only have one trig ratio. And then be in terms of the same angle as well. So x and 2x are not the same. We want them all to be in terms of the same angle. Yeah. So let's go. Okay, cosine 2x equals cosine x. Oh, well, that's interesting. So you could really use the unit circle and imagine when would the cosines be the same and stuff. But that's a little challenging. Okay? We're going to apply some trigonometric identities. So I know cosine 2x is the same as cosine squared x minus sine squared x, and that's going to be equal to cosine of x. Okay? Just using my identity there. I just check it, make sure that I'm right. Yeah, that's right. And then I'm going to turn it all in terms of the same angle, the same trigonometric function. So sine squared x, I just remind myself that sine squared x is equal to 1 minus cosine squared x. So this is minus 1 minus cos squared x. And hooray! I'm finally now all in terms of the same angle and the same trigonometric argument. The same trigonometric ratio. So now I just combine all this stuff. So this gives me 2 cosine squared x minus cosine x minus 1 equals 0. People see how I got to that line? I did two things at once, which, like, why do I do that? Why do I hate writing an extra line so much? I'm subtracting cosine x from both sides. That's how I got that one there. I have minus 1. That's that one there. And this one is minus minus, so that's why I have two of those there. Okay? Now, I'm going to do this fancy thing. Let cosine of x equal b. Okay? So this gives me 2b squared minus b minus 1 equals 0. Yay, it's a quadratic I can solve. 2b squared minus 2b, or not 2b, we're going to add b, minus 1 equals 0. Notice, that's the same thing as I have down here. I just split up my minus b into minus 2b plus b. It now factors by grouping. So here's one of my groups. 2b times b minus 1 plus 1 times b minus 1 equals 0. And then we end up with 2b plus 1 times b minus 1 equals 0. I'm having heebie-jeebies because I feel like I've made an error somewhere. No, it looks good. Yeah, I just had different solutions before. I made an error before when I was practicing for the lesson. Okay, so now I have this one equal to 0, so 2b plus 1 equals 0. So that is to say b equals negative 1/2, or b minus 1 equals 0. So that is to say b equals 1. So that gives me two different sources of a solution. I go back to this, and now I say, okay, so cosine of x equals negative 1/2. And then I have to use my visualization of where that happens. So that's going to be over there and over there, where I have this one or this one. Okay, where this is 1 and this is 2, but that's negative. Okay. So, what angle does this?
135.
Not 135, because it's the 1, 2, root 3 triangle. It is indeed 120, but in radians, what's that? It's 1/3 less than 1 pi, so 2 pi by 3. So this is 2 pi by 3, and this one is minus 2 pi by 3, or this is 4 pi by 3. So we have x equals 2 pi by 3 and 4 pi by 3, okay? Or cosine of x could be equal to 1, and cosine is equal to 1 for these situations. Boop. That's where cosine is equal to 1. Okay, at 0 degrees, or this one, 360, or 2 pi. So then, we're going to proudly write out our solution. Therefore, x equals 0, comma, 2 pi by 3, 4 pi by 3, and 2 pi. And then, how do you suppose we check our work in Desmos, everybody? Not on a test, but during our practice, so that we're consolidating our understanding? Sorry? You can just type it into Desmos. Cosine, oops, cis. I am a cisgendered male, if that was. Cosine 2x equals cosine of x. Okay, and then we zoom out, and you're just going to turn this one off. Okay, so we have it's equal there, and it's equal there. 2 pi by 3, 4 pi by 3, and 8 pi by 3. Oh, but that's past 2 pi. For some reason, it's not giving me the 2 pi solution, which is real weird. That's really weird. Because it absolutely is a solution. I am weirded out by that. Huh. Usually it's real reliable, everyone. Why isn't 0 a solution? Cosine of 2 times 0 is absolutely equal to cosine of 0. That's so weird. Why it's not showing us that, I have no idea. Huh. Okay, anyway. It's generally quite reliable. Sorry about that. I don't know why Desmos is doing me dirty there. Okay, let's try this one. What manipulation can I do here to get this all in terms of the same variable? Sorry, the same trigonometric argument. Yeah?
Sine squared x is 1 minus sine squared x?
Is 1 minus cos squared x? Yeah, good. So we're going to substitute here 3 cosine of x plus 3 equals 2 times 1 minus cos squared x. And then we manipulate here. So then we're going to subtract 2 from both sides. So that, and then we're going to add 2 cosine squared x to both sides. Oh. Huh. I don't know why Connor keeps talking. Okay. Here. I'll show you. Oh.
Why don't you count cos?
Now I want to set this equal to 0. So I subtract 2 from both sides and I add 2 cosine squared x to both sides. And then we get this expression 2 cosine squared x plus 3 cosine x plus 1 equals 0. Let's do a quick substitution. Cosine of x equals n. So that gives us 2n squared plus 3n plus 1 equals 0. Saves us a lot of writing. 2n squared plus 2n plus n plus 1 equals 0. 2n times n plus 1 plus 1 times n plus 1 equals 0. Okay, there's our group there. There's our group there. 2n plus 1 multiplied by n plus 1 equals 0. So that is to say n equals minus 1/2 or n equals -1. We've already seen where cosine is equal to -1/2. That's at 4 pi by 3 and 2 pi by 3. So that is to say x equals 2 pi by 3. This is exactly the same as the last one. And 4 pi by 3. But if cosine of x equals -1, we're going to find that that's true over there, where we have 180 degrees. Cos 180 is -1. If you've memorized your trig function and know it looks like this, there's 180. It's the minimum value of cosine, it's -1. But when we look at it on the unit circle and we rotate all the way over there, that's where the adjacent side, the x value, is equal to the hypotenuse, or -1. So this is pi. X equals pi. And it's the one case where there's only one solution there. So there's only one spot where it reaches its minimum, not two. And it doesn't show up twice in the period. So there you have it. So therefore, x equals 2 pi by 3, 4 pi by 3, oops, I didn't write them in increasing order, and pi. So those are the three spots that it does it. Let's write this into Desmos and see what it shows us. Three cosine x plus 3, I think it was, equals I forget it entirely. 3 cosine x plus 3 equals 2 sine squared x. There. So we get 2 pi by 3. It doesn't show us pi again. That's so weird. Okay. So, watch this. If pi is absolutely a solution, so if you're confused, you would just write 3 cosine of bracket pi is minus 3 plus 3 is equal to 0. Okay, so the left-hand side is equal to 0. What happens if I input this, like, sine pi? The sine of pi is 0. So 2 times the sine squared 0 is 0. So I'm not sure why it's not showing it to us. It's very odd, and it was really cooperating with me earlier, and right now it's not cooperating for these particular problems. But yeah, just know that if you're checking in Desmos, it's good to learn this on the fly. When you're checking a 0 solution, it's not showing us those in the trigonometric ones, which is very interesting, but who knows why. Okay, suppose we have one like this.
No, I implied that here.
Okay. And then here, we want to find all possible solutions. It's good to note here, cosine of x cannot be 0. Therefore, we have x is not equal to 0 or pi or 2 pi. Because any of those would give us a denominator that's equal to 0, and we can't have that. We have to exclude those from the solution. Yeah, do you have a question? Or
Is cosine of 0?
cosine is 1, yeah, you're right, yeah.
Okay.
So yeah, thanks for pointing that out. I had a little, that would be if this was sine. So x is not equal to pi by 2 or 3 pi by 2. Okay, those are the ones that we have to eliminate. That's worth a mistake. So you could put one up on the board if you want. Okay, so now, in order to simplify this, I'm just going to express all this, just move that cosine over. So one thing we can do is just factor this. So we're going to have 2 sine squared x over cosine squared x minus 3 cosine x equals 0. So just move that over to the other side. Create my common denominators. This would be I don't know why I wouldn't just do it that way, actually, in this case. I would just multiply here by cosine x, because we know that cosine x is not 0. So go ahead and multiply both sides by cosine of x. For some reason, that is erasing very slowly today. So if I multiply, I get this is equal to 3. And so I have 2 sine squared x over cosine of x. This is after multiplying both sides by cosine of x. And then convert that one into cosine. So this is 2 times 1 minus cosine squared of x equals 3 cosine of x. Multiply both sides by cosine. I get everything upstairs. We say let cosine of x equal v. So we have here, multiply this in. 2 minus 2v squared equals 3v. We're going to shift everything over to the other side. So we have 0 equals 2v squared plus 3v minus 2. Okay. We want to multiply to minus 4 and add to 3. So those are 4 and negative 1. So 2v squared plus 4v minus v minus 2. We factor. 0 is equal to 2v multiplied by v plus 2 minus 1 times v plus 2. Okay? This gives us our final factorization of 0 equals 2v minus 1 times v plus 2. And then, if this one is true, then that means v is equal to 1/2. That one can give us solutions. Cosine of x can equal 1/2. And we're going to find our solutions there. How about v plus 2? Cosine of x equals -2. What solutions does that give us for x? What values in radians give us a cosine value of -2? None? You're meaning that part of this equation doesn't give us any solutions? Yeah, because cosine is at its maximum 1 and at its minimum -1. So this is outside of that range, so this has no solutions. Oops. So we go back here. This is the only one we need to tangle with on our domain. So we have cosine of x equals 1/2, and that happens over here and over here. So we are positive pi by 3 and negative pi by 3. That's pi by 3. So we are x is equal to pi by 3 or 5 pi by 3. Because that's minus, so that's 2 pi minus pi by 3. And those are all of the solutions. This one's going to cooperate when we write it into Desmos. So let's take a look at it. 2 tan squared x equals 3 secant x. Oh, wait. Desmos doesn't like you writing these. You have to write the reciprocal trig. So we had 2 tan squared x equals, I think it was 3 over, was it cosine? 3 over cosine x. There. So we have pi by 3 and 5 pi by 3. Our domain was up to 2 pi. We got both solutions, so the people rejoice. Yay. And that one's cooperating. What a delight. Okay. And then this one here. This one I want to talk about. This was the one that sent me down the hall to talk to Mr. Beck and Miss Metherall, saying, how are you teaching these students about this one? Tan x sine x equals sine x, because I have a different perspective. Here is Miss Metherall's perspective. Never cancel common terms on the left side and right side, because you're going to lose some solutions. And I went and I said, I can cancel them on both sides and I'm not going to lose solutions. And I want to teach my students my way, but I also want to teach them your way so that if you have the good fortune of winding up in Mr. Beck or Miss Metherall's calculus classes, that you'll understand their methods. So this is their way, okay? Do not to cancel both sides and like divide by sine x on both sides, but to subtract sine x from both sides. Okay, and then we end up with this expression, tan x sine x minus sine x equals 0. Okay, and then if this was like a quadratic, we'd have no problem. We just factor. So I'll just factor. Factor out your sine x. Sine x multiplied by tan x minus 1 equals 0. This gives us two sources of solution. Maybe sine x equals 0, and that would solve this equation. Or maybe tan x minus 1 equals 0, and tan x equals 1. And that would give us solutions. Great. We found both sources of solutions here. That can give us solutions, and that can give us solutions. So this one here, sine x equals 0. This is the situation on our unit circle when we're over here or over here. Okay? Where the the y value of the angle is exactly 0 and the line is on the x-axis. So that is 0 or 2 pi over here. That's this situation. Or pi over here. That's that situation. Okay, so we have here x is equal to 0, comma, pi, comma, 2 pi. And because these are inclusive, we have all three. So we have three solutions from that. Tan x equals 1, on the other hand, gives us a different source of solutions. Tan x equals 1, it looks like this, where we are either the 45-degree triangle, the 1, 1, root 2 triangle, so that's pi by 4, or we're down here. Not if it's not handy. No, I have these. Where's that work? Okay. Welcome. And this one is 5 pi by 4. I know that one's 5 pi by 4 because CAST rule, C-A-S-T, so I'm looking for a positive one. I know it's the same reference angle, so that's my pi by 4, added on to pi. So pi plus 1/4 pi is 5/4 pi, so 5 pi by 4. So this gives us x equals pi by 4, comma, 5 pi by 4. And I said, I do this differently, you two. And they were like, yeah, your way's fine too, but we teach it our way because the students make fewer errors. And I'm like, fine, I'm going to teach them both ways because I like doing it my way. So this is what I do. Tan x sine x equals sine x. I am going to divide boldly both sides by sine x. But when I do that, I have to make sure that sine x is not equal to 0. If sine x is equal to 0, I just divided both sides by 0, and that wouldn't make sense. So then when I do this, whenever I do this, I have to also consider, is sine x equals 0 a solution? And it is indeed. I just look at it and I'm like, something multiplied by 0 is equal to 0. So yes, it provides me solutions, so I go investigate them. That's it. And then I get here tan x equals 1, and that's the other half of my solutions. So when sine x equals 0, I have my solutions from that, and I investigate them. That's all. Okay, another example here. We did that example already. That's good news. We did that example. Yeah, they're doubled up in this PowerPoint. We did that example. So practice problems. Yay, we made it, everybody. 10 minutes left. Okay, so we need some time to practice these, of course. So you're going to have some time tomorrow to do your practice and things. We did schedule, do we schedule the test for like 3 days? Thursday, Friday, Monday? Yeah, is that what we did? And there were like people missing Thursday, or there were people missing Friday, there were people missing Monday? B? Yeah? Okay, so we'll talk about that in a second. So practice and let me know how it goes. Yeah, I'll be around. I'm coming.